subgroup, the cosets. There's some kind of structure that goes on around the cosets, and then there's something that goes on in the normal subgroup. And like this, you can kind of build from pieces every finite group. But what are the pieces? The pieces are called simple groups. And then they're the groups that you can't split into a normal subgroup and factor group, kind of. Okay, so simple groups are the finite, well, we're talking about finite, but it applies to infinite as well. The simple group is one that doesn't have any normal subgroups other than itself and just the identity. That's the idea of a simple group. And there's a big, and I said that there's a big catalog that took 100 years to build of all the finite simple groups. Yeah, there are infinitely many of them, but there are only finitely many types. And then there are some extra ones that don't belong to these infinite families, and they're called sporadic groups. So you can look it up. It's quite a fun thing to look up, even though I don't understand it. But the first example of a simple group, which is non-abelian, was found by Galois, and it's the alternating groups on at least 5 letters. And we set out yesterday to prove that they are simple. And the way of proving it was like this. So first we said that if you take all the 3 cycles that appear in that alternating group, and you look at all their products, you get the whole group, and you won't be missing. That was the first lemma. And the second lemma was that, in fact, you don't need all the 3 cycles. You can fix 2 numbers between 1 and n, I and j, and then you take all the cycles, I, j, and something else. So you only get n minus 2 different cycles, and that already generates the whole group, whereas there are plenty of 3 cycles. That was the second lemma. And then using that, we proved that if you find a normal subgroup which contains a single 3 cycle, then it contains all 3 cycles like this. Okay? Because it's normal, it's closed under this conjugation operation, and so you can find any 3 cycle that fix I and j, and b is anything else. So it's there, and then you use the previous lemma that you have all such 3 cycles, so you have to have the whole group. Quite a lot we did today. And then the final thing is, now we knew that if a normal subgroup contains a 3 cycle, it has to be the whole group. So the last bit in the proof of showing that there are no normal subgroups other than the whole group and just the identity is to show that if you have a normal subgroup which is more than just the identity, then there has to be a 3 cycle. And then you have a 3 cycle, you have all 3 cycles, you have all 3 cycles, you have the whole group. Okay? So that is the last thing to prove. That's where we are. Good morning. I fixed it.
Hello.
Right. So this is a bit of a trick proof. It's not obvious how one would do it. The other proofs were kind of obvious, but this one is perhaps a bit more sophisticated. So well, we have that n is not just the identity. Okay? It's a normal subgroup. So because it's more than just the identity, it contains some sigma, which is not the identity. That's obvious. Now, we can write this sigma as a product of disjoint cycles. So we know from when we were doing permutation groups that any permutation can be written as a product of disjoint cycles, any order. The cycles are kind of defined uniquely. Now, when we write it, there are only 5 things that it can look like, 5 ways that it can look. So then sigma looks like one of the following. The first possibility is that sigma is a 3-cycle. That's quite a good possibility because we want a 3-cycle, and if we found a 3-cycle, then we have a 3-cycle. But it's not the only possibility. It can happen that sigma is, well, you write some cycles, tau, and the last one that you finish with is a long one. So A1, A2, AR, and R is bigger than 3. So we can say that sigma contains a long cycle. Well, tau is all the other cycles. Okay, so I just look at the last one. I write it as a product of disjoint cycles. I look at what the last one is. And the last one can be a long one. Okay, and tau is the rest of it. Well, I'm actually not looking at just the last one. I just arrange them so that they are increasing in length. So if it contains a long cycle, because the disjoint cycles, I can commute them as I want. Okay, so they can be in any order. They're disjoint. And so if there is a long cycle, I just put it at the end. So either it's a 3-cycle, or it contains a long cycle, or maybe it doesn't contain a long cycle and it contains more and it's more than just one 3-cycle. So then the third option is that it contains at least 2 3-cycles. So again, I put these 2 3-cycles at the end. And I'll call them A1, A2, A3, A4, A5, A6, which means that sigma contains at least 2 3-cycles. And there's a fourth option that in the product of disjoint cycles, there's exactly 1 3-cycle, and then there are other things that are shorter. So transpositions. So sigma can be some product of transpositions, and tau is a product of transpositions. And the fifth option is that it doesn't contain any 3-cycles whatsoever. But then, possibly the star is the identity. Yeah. Yeah, and tau is a product of transposition. Okay, so now let's.
So the book says for that last one,
Yeah.
even transposition.
Yes.
That.
I don't know yet.
What?
I don't know yet. Can't remember if it's important. I don't think so. But it's true. Okay. So let's now make sure that we all understand that one of these cases has to happen exactly. Do we? So when you write it as a product of disjoint cycles, okay? So question number one: is it just a free cycle or not? If it's just a free cycle, then it falls into one. Okay? So if it's not just a free cycle, then the next question is: does it have a cycle which is more than length 3? Okay? Does it have a 4 cycle, 5 cycle, 6 cycle in it? And if it has, then it falls into 2. Okay, so now all the permutations that are just a 1 free cycle, or that contain a longer cycle than 3, we'll go with. So now we know that if it doesn't fall under 1 or 2, it's a permutation which you write as a product of disjoint 2 cycles and 3 cycles. So no longer cycles. Okay? Now, how many free cycles does it have? Well, there are 3 possibilities for how many free cycles it has. Yeah. Either it has no free cycles in that thing at all, or it has exactly 1 free cycle in it, and the rest are shorter. So what is a shorter cycle? It's just a 2 cycle, that's a transposition. Or it has 2, 3, or more free cycles, and in that case, tau is product of some cycles. We're not saying it's transpositions only, but there are at least 2 free cycles that we can write at the end. Is it clear now? Yeah. One of these things happens. In fact, we can actually say that this tau is not the identity, but here it might be the identity. Now, okay, well, why does it have at least 2 transpositions? It could just be that there's only 1 transposition. But it cannot be that it's only 1 transposition because we're in the alternating group. So they have to be written as a product of an even number, no matter how you write them. It's a product of transpositions, there's going to be an even number of them. Okay? So you get an even number of transpositions. So yeah, it's right that tau is the product of an even number of transpositions, so I don't think it's necessary for the proof. Okay? And this is also an even number of transpositions because a free cycle is an even permutation, so this also has to be. Okay?
Why do you say it's an even number of transpositions with tau?
Because sigma is in the alternating group, and alternating group only contains products of even numbers of transpositions. Okay? Which is half of the symmetric group. The odd permutations are not in there, by definition. Okay, so now that hopefully is clear. So now, in each of these cases, we want to show that there is a free cycle in it. So which case is the easiest of all?
1.
Yes, indeed. So 1, we're happy.
Sigma is a 3 cycle, and we are doing. Oh, we're happy.
Okay, we found a 3 cycle and we want to show that there is a 3 cycle. That's the claim. We're showing that n contains a 3 cycle. If we found it, but we take any element, and if it happens to be a 3 cycle, then there's nothing else to do. But it doesn't have to be. So maybe it looks like this, and then that's starting to be. Yeah, you don't want to go through this.
I just don't want to look.
It is horrible. Yeah. So I'll just show. I won't go through everything, obviously. Okay. So number 2. So we're in case 2 where we have a long cycle. Okay. So I take 3 elements from the cycle: A1, A2, A3. Now I times it by sigma. I don't know whether that's in the normal subgroup or not, but what I do know that is in the normal subgroup is if I times it by the inverse. And why is that? Well, that is because a normal subgroup, if you take something from a normal subgroup and an element of the large group, any element of the large group, and times it by the element from the left and by its inverse from the right, you get something in the normal subgroup. That's one of the definitions of the normal subgroup. So this is definitely in the normal subgroup. And also if I times it by the inverse of sigma, which is in the normal subgroup, so this is an element in it. So N contains this product. So now if I, well, look at 2. What is sigma? Sigma is tau times this long cycle. Okay. So what do I get? A1, A2, all the way to AR, inverse, tau. How do you write tau? Tau inverse. Times A1, A2, A3, tau. So that's this, times sigma, so that's A1, AR, times tau. Oh, you're right. Doesn't matter. Times A1, A2, A3, and run out of space.
Yeah. Can I clarify?
Yeah.
A lot of A1s, A2s, and A3s, are they same or different?
They're taken from here.
So they are the same.
Yes, so I look at the long cycle, I take its first three elements.
Cool.
Okay, and I do this. So I've run out of paper. Did everybody read it okay? Delete this.
And then what? Oh, I've written down. So A1, A2, A3 is an element in AN. Yes. So.
Yeah, so A1, A2, A3 is an element of AN, but not necessarily of N.
Yeah, that's what I'm
But this, all I've done is I've used this kind of information about what sigma is to plug it in. So if I do sigma inverse, I get backwards this inverse times this inverse. And if I do sigma, I get tau times the long cycle, because that's what it is. Now, what this is if I do the inverse of the long cycle, I get that going backwards. Okay, so A2. That's the inverse of the cycle. Can start anywhere you want. I mean, the cycle is cyclic, right? You could start from A4.
I'm just going to put A1 at the end for my notes.
Okay, then A1, A2, A3.
It's theoretically.
They A1, A2, all the way to AR, and then A3, A2, A1.
Okay.
Now I've fixed it.
And where did the towels go?
They vanished.
And why?
So, what is A1, A2, A3, and tau? Many things, so it's a stupid question.
Yeah.
But one of the things they are is disjoint cycles, the disjoint products of cycles. So if they're disjoint, they commute, we know that. So you can swap A1, A2, A3 with tau, and then tau inverse tau back. Okay, so that's where tau is going. Okay, now we can work this out. So where does A1 go? A1 goes to A3, goes to A4, goes to A4, goes to A3. Okay, A1 goes to A3. A3 goes to A2. A3 goes to A1. Oh.
A3 goes to A2, which goes to A3, which goes to A1, which goes to A3.
Okay, A1, A3 goes to AR.
Yeah, which goes
AR goes to
A2,
AR,
which goes to
goes to A1, goes to A2, goes to A1. Okay, so that closes the cycle. Is everybody still on board? Or am I doing it too slowly? A2 goes to A1, goes to A2, goes to A3, goes to A2. A2 goes to A2. A4, where does A4 go? A4 goes to A5, goes to A4. And everything else goes to +1, goes to -1, so everything else stays. So that's it. All the other ones are just one cycle. Okay.
Oh,
So
wait,
that's a
it's
3 cycle. Yay.
it's like it's much
Did it?
more complicated than it is just because it's all like subscripts and I objected.
Well, we're happy. Well, we wanted a 3 cycle and we found one.
Woohoo!
Well, I told you from the start that normal subgroups were excited.
That was me being happy. Yay!
Okay, so I don't want to go through everything because it quickly gets boring. But in case 3, we have the product of 2 3 cycles. Okay, so by a similar measure, we can do A1, A2, what does it want me to do? A4 times sigma times A1, A2, A4 inverse times sigma inverse. So this is for a similar reason as before, this is contained in N. Okay. Sigma is in N, conjugate by any element is in N, times something in N is in N. Now, if you work it out, it turns out to be, so again, because the taus are in the right positions, the tau and tau inverse will vanish, you will be left with things that only contain A1, A2 up to A6, and when you work it out, you're supposed to get A1, and I checked it at some point, no, A1 goes to A4, that's not a 3 cycle, so what do we do?
It's
Indeed, we apply the previous case. So we already know that in case 2, if there is a long cycle, then there is a 3 cycle. If there is 2 3 cycles, there is a long cycle, so there's also a 3 cycle, so apply case 2.
I'm a bit. Haven't we multiplied that by?
Okay, you asked for it.
No, don't do it. But like, how do we know that that is contained in sigma?
What?
That long
An N?
is an N. Because that's
Yeah.
Why are we not? Then we're on the 2
Oh.
3 cycle. Like, you want this one.
Yes, you want to have a permutation which is only a 3 cycle and nothing else. Yeah? If you have a permutation which is exactly 1 3 cycle and nothing else, then you have by the previous lemmas you have it. But it's not enough. We didn't prove yet that if you just have a permutation that somewhere inside of it has a 3 cycle, that's enough. But that kind of is these 2 cases, 3 and 4. But we've not got that yet. We've only got that if you have a permutation which is only a 3 cycle and everything else is fixed, everything else is 1 cycles, then we're happy. So that's what we're trying to achieve in all those 5 cases. The first case, it's immediate because if sigma is just a 3 cycle. That's exactly what we want. In the second case, we have to do a bit of work. In the third case, we have to do even more work. And what we get from here is not a 3 cycle, but what we get from here is a permutation which looks like that, like this sigma. So then, and once we've got that one, we can do this, and we've got a 3 cycle. Okay? So that's case 3. And I didn't quite do all this. Well, it's in the book, I think. Or is it not? I don't know. Anyway, it's not very hard to do. You just plug in what sigma is from the case, and the tau inverse, they will commute with something, so they will vanish. So that it's not very good at all. And number 4 was number 4. We have something that just ends in a 3 cycle. In this case, what is it? You just square it. Oh yeah. So n, because it contains sigma and it's a subgroup, it also contains sigma squared, and it turns out that sigma squared is, well, tau, A1, A2, A3, and same thing again. And that is well, again, this 3 cycle and this tau are disjoint, so they commute, so I can do tau squared and tau squared, because it's just a product of transpositions. Its squared is the identity. Disjoint transposition. Okay, so transposition squared is the identity. So that's this. And then case 5 is kind of tricky. So again, sigma is in N. I do conjugation by A1, A2, A3. And sigma inverse. So we've seen a trick like this before, several times. So this is in N. So what does this do? Okay, sigma inverse is A1, A2, A3, A4, tau inverse Oh. So that's sigma inverse. Now A1, A2, A3 is already there. Sigma is tau A1, A2, A3, A4. And then there's A1, A2, A3 inverse. Okay, so tau is disjoint with this. They vanish. Tau we can ignore. Where does A1 go? Goes to A3. Where does A3 go? Can't follow. Okay, so A3 goes to A2, goes to A1, goes to A2, goes to A1. Yeah, A2 goes to A4. A4 goes to A2.
Oh, wait, some of those are backwards.
And that's it, that's everything. So that's not a 3 cycle.
Pretty sure.
That's disappointing.
I'm sure it'll become. It doesn't become. So just does you have to create a view?
Oh, we're just gonna force it. Oh. Just that.
Yeah.
Yes.
Can you promise us that we end up going up to learn something?
No. Now, so we've got something in N, but it's not a 3 cycle. But there is now the trick comes. Okay? So the tricky bit is because we're assuming that the little n, the number of letters that we're using, is at least 5. There is going to be one which is not used in these. Only used in 4 here. So there's going to be some B, which is one of the n letters, and it's not A1, and it's not A2, and it's not A3, and it's not A4.
Yes.
And then A1, A3, B inverse. That's not, we don't know whether that's an element of N or not. We don't know that. But if we use it for the conjugation of the thing we know is in N, so A1, A3, A2, A4, and then A1, A3, B, we know that this is contained in N. Right? There's a normal subgroup. So take something from the normal subgroup, times it by something from the left, and its inverse from the right. Anything in the group, I get something in the normal subgroup. Always the same trick. It's a normal subgroup. So when we have this, we can this is in N. This is in N. So the product is also in N. So what's this? Where does A1 go? Don't read it.
Oi! Three.
Okay, A1 goes to A3, A3 goes to B, B goes to A3, so A1 goes to A3. Where does A3 go? Goes to A1, goes to A3, goes to A1, goes to B. Because it's in the
Oh, nice. I hate it when you talk about the end of this.
Didn't you just write it down yourself?
No,
Like, what would that write it?
So where does B go? B goes to A1, goes to A3, goes to A1. Okay.
It's a 3 cycle.
How do we know? A2 goes to A4, goes to A2. Okay, A2 goes to A2. A4 goes to A2, goes to A4. Okay, so it's a 3 cycle.
It's in the book. It's real.
Just in time for the theory.
Oh.
Theorem 1011. For any greater than or equal to 5, the alternating group is simple. So how does the proof go? Well, you take a normal subgroup, which is not the identity. You want to find one which is not trivial. But if it's not the identity, it contains a 3 cycle by limit n10. If it contains a 3 cycle, yeah, it contains a 3 cycle, then it's the whole group by limit 10.9. Yeah. Is there anything else in chapter 10? Proponents?
The historical note.
Yeah, read the historical notes. Not now.
Sage can easily data.
Yeah, but you voted not to do any Sage anymore, so
We did.
Did we?
Well, we said, can we move the class forward clause? They said there's no computer, and we all said, that's fine.
Oh,
They
okay.
didn't.
Yeah. Yeah.
so there's no more Sage. There's exercises on Thursday. Anything else you need to know about normal subgroups, simple groups? There are a few submission problems. I think one can see them as a kind of practice for the exam, perhaps.
Is that
Please say this is not. It's proof.
Yeah.
Yeah. You're gonna remember.
You do